So, good morning, everyone. Thanks for joining this second day. I just wanted to show in that website that I shared. Let me share here on the chat again. Now, I just adjusted the times here. I know we ended a little bit earlier yesterday. It might happen the same today. We'll see. But I just want to show that I've added the recording from yesterday here. So you can access, you can watch directly here, or you can, just open this on YouTube to watch. But the slides are here. There's also the link here if you want to download and watch on your computer. You can do this as well. And slides for today are also located here in day 2. And as we go, I'm gonna, keep adding resources here in case, you're interested in looking to more details about, any of the topics we've been talking. There's, some of these are actually courses or, crash course by Google or Development Seed. So I'll just keep adding resources here at the bottom of the page. So let me present. Let me share this link as well so you all have access. Put it in the chat. Okay. Can everyone see my screen? Fine?
Fine, yes.
Great,
Fine,
okay.
I can see. Yeah.
Thank you. So after yesterday, we're gonna do a recap, but the goals for today is to dive a little bit more, in depth regarding neural networks. We're gonna talk a lot by, terminology. We're gonna learn a lot about the terms that, people use, so you all get used to it. When you read something about, machine learning model, you know what people are talking about. We're gonna look into, model structures and architectures, and also we're gonna talk about advantages and disadvantages of using neural networks. Those are the main objectives of the day. Before we start, what is a webinar without a Menti survey, right? So I just want to do a quick survey with you all. So you just need to go to menti.com and use the code here, 523309. I'm also going to post in the chat so you have, and this is just to get just to see how you all are feeling regarding training. So if you open the link and put that code, you should be seeing, a question, how confident are you with the concepts learned yesterday? And then you can vote. If you're not able to go into this, so let me know. And it's here at the top as well, menti.com and then 523309. Okay, we got one result, and don't worry, this is anonymous, so we won't know who's responding. Okay, you got 4 people. Five. We have about a third of participants. So we're halfway there, a little bit more halfway, but can already start seeing that, most people are in the middle here after yesterday. And I know yesterday we only like kind of touched, the concepts. We didn't really go in depth. And okay, we have 12 people. I think that should be everyone, because there's me, there's Maria. Okay. Yeah, so that's good. Yeah, thanks for answering. This helps me, get an understanding of how you all are feeling and if it should be more detailed or not. But it seems, I think with neural networks, this will improve a little bit because we're going to talk more about neural networks today. But we can definitely, the reason I asked yesterday, and I'm going to reinforce this today to do like a presentation, is that we can have, you guys, just making something that, sharing what you've learned, share the points of confusion, any questions that you might have. So we're going to work on that. And then the second question really quick is regarding the pace. So if I was, going too slow, or if it was the right pace, or just too fast. Okay, we got 5 people. Okay, that makes me feel better. Thank you. uh, it seems that, I guess the compared with the answers from the previous questions, that, the topics might be really just complex and, just complicated. But I'm happy to see that, it was mostly the right pace. And, feel free, don't hesitate if you want to interrupt me in the middle, if you want to ask anything, or sometimes I do talk too fast, so feel free to interrupt me. But this is good. We have 11. Let's just wait a couple more seconds to see if anyone else will add. Okay, seems like no one else. That's okay. We saw majority was the right pace. So those are only the 2 questions I have. Let me close. Okay. Thanks for participating. And I can go full screen now. Okay. So just a quick recap of yesterday. We did look into artificial intelligence, the definition of it, the types, examples. We looked into machine learning. Specifically, we discussed what is supervised learning or supervised classification, unsupervised classification, semi-supervised, the reinforcement learning, and neural networks. So just a refresher, this is an example of neural networks where you have your input layer, your hidden layer, and then the output layer that this can get fed into a new input layer. And then, the summary of yesterday was focusing that, it's a nesting process. So you have artificial intelligence, which is the technique that enables machines to mimic human intelligence. Then machine learning, which is a subset of AI, where the computers learn how to improve based on experience. And then deep learning, which is a subset of machine learning, where you have not only one layer, you have multi-layer neural networks. We're going to talk about more about deep learning in neural networks today. And we went through, all the definitions here: supervised classification when you have labeled data and the machine uses that to learn. Unsupervised when it just uses the data as is. It doesn't have any information, no label, so it just learns based on patterns or features. We gave examples of, dog and cats. Even though you might not know what a dog or a cat is, if you look at a dog or a cat, you can, identify similarities between the dogs and similarity between the cats. Then semi-supervised, you have a mix of the two. You do have small amount of labeled data, but then you have a large amount of unlabeled data. And then reinforcement learning, we talked about, playing chess or training your dog, right, to learn how to use the bathroom in the right place, for example. And the neural networks we just introduced. So that was the recap of day one. So this is something I did not go into yesterday, but I do want to show today. Just it's the overall process of machine learning. So this is not going into any specific algorithm or model. We're just talking about how it should be done, the process. So you have a few steps. One, you gather and clean the data, which is going to be your sample, and then that represents your large population, right? For example, we thinking about the crop mapping process, our sample data are crop polygons, right, that you all collected during the reference data collection campaign. And an important note is, yes, this step can at times take the longest time because it was mentioned yesterday that you need good data so that your model can perform well. So we need to guarantee that your data is good. Then step 2 is to learn and understand the data to figure out trends and patterns. That's what the model does. We talked about weights, figuring out which weights to use depending on what you're trying to predict. Then you build the model that understands the data and make decisions on this data. And then we're going to talk a lot about this today. Not a lot, but a little bit about, training data and test data. Usually there's a breakdown between training data and test data. We're going to talk about that. So you have training data to feed the model and train the model, and then you have the test data so you can validate the model. And then, based on the results of this, then you can repeat the process again. So you need maybe to collect more sample data or to increase your, study area or to include more representation of the landscape or something like that. And we talked about this when we were overviewing the crop mapping process in Cambodia. We had to do a little bit of cleanup of the data collected. So this is, just emphasizing that it's an iterative process. But, this is the overall workflow that, using a model people should do. Then just as a refresher, we saw this yesterday, what is neural network, apologies. So it is a branch of machine learning where algorithms learn independently from excessive amounts of data. So this is one of the advantages. We're going to see this later. But compared to traditional machine learning, the advantages of a neural network is that you can take an excessive amount of data. So big data here that we are talking. And then similar to humans, these algorithms get smarter with experience by gathering, processing more and more data. This is the MNIST database. This is one of the most popular deep learning data sets out there. It's a data set where you have written digits and contain training set of 60,000 examples of these written digits, and also a test set of 10,000 of these. So this is a very good data set to use to learn the concepts, to try to build a model. And it's based on a real world problem. It's just a machine trying to identify which number it is. So I left here a link for a tutorial on this data set, and this is based on TensorFlow on Google Colab. So if you guys want to take a look at that, I just wanted to share that this is available, if you want to start slow. And then we talked a little bit how neural networks work. So they do discover pattern and structure behind these vast amounts of data, and the model consists of multiple layers where data is processed. So you have your labeled photos here. You have a cat and a dog. It goes through these layers. It has those weights. It learns patterns, features of these labeled data, and then in the end you have your output, which in this case is classifying as a cat. And we're going to talk about, so this would be the input layer. As we saw, these are all the hidden layers, and then the output layer here at the end. So again, just reinforcing, we just talked about with this, we have three main elements in neural networks: the input layer, which is the data we want to analyze; the hidden layer or hidden layers, or they are also called nodes, which completes the computation; and then the output layer are calculated results. So we're going to talk about this. We have a simple neural network, which means that it only has one hidden layer, but a deep learning neural network, it contains more than one hidden layer. We're going to talk about these terminologies because a lot of people use this interchangeably. So people say neural network referring to deep neural network. So we're gonna be seeing this today. So let's go straight into terminology and architectures and structures of neural networks. So yeah, I want to emphasize the concept of training and test data. So training data is the subset of your sample or your data that you want to train the model, and test set is the subset of the data to test the training model. So you cannot once you decide, once you've trained your model, you should not use the same data set to test the model. So we want to break the sample data into these two sets. And usually, there are variations, but usually people use like 80% for the training set, 20% for the test set. But, you can also see people using 70% for the training set and then 30% for the test set. And training just means that you're creating, you're learning the model. So that is what we saw before. You show the labeled examples, and that enables the model to gradually learn the relationships between the features and the label. So you do want to make sure that your test set meets these two following conditions: that it is large enough to yield statistically meaningful results. So you don't want to have a very small test data because that can be biased, meaning that, for example, in our crop mapping work, our trained data contains many different types of crop types, right? Croplands. So we want to make sure that our test data will also have different types and not only focus on, I don't know, for example, cassava, right? We want to have a good representation both in the training set and also in the test set. And this is exactly the second point here, that it is representative of the data set as a whole. So in other words, you don't pick a test set with different characteristics than a training set. So the way people do this is you have your entire sample data set, and then you randomly assign some points to the training set and then to the test set. So that way you make sure that you have a good representation of your sample in both sets that you're going to use. So this is just a schematic. You train your model using training set, evaluate your model on the test set. You tweak a little bit if you don't get very good results. Test set, you're gonna do this again until you get good results, and then you pick the model that does best on the test set. So never using the training set here to pick the model, always using the test set. But there is a variation as well. We will be doing this for accuracy assessment. Instead of only having training set and a test set, you also have a validation set, and that's used to evaluate results from the training set instead of using the test set for that. So then you use a test set to double check your evaluation after the model has passed the validation set. So this is just a double check of the training set. So it's using it's like having two different test sets. That's pretty much what this third validation set is for. And this avoids overfitting. We will be talking about overfitting and underfitting later today as well. But that's just keep that in mind. Avoid overfitting, and then when we talk about this, we can remember the validation set. Why have the validation set? So this is just the adaptation. You train the model with the training set. You evaluate your model with the validation set, and then you're going to tweak the model if you need to tweak depending on the results. And then you pick the model that does pass on the validation set, and then you do a double check using the test set here at the end. So this is just making sure that it's really the model is really predicting what it should predict. Also, training and loss. So as I said, training simply means learning, determining good values for all the weights from the labeled examples. And in supervised learning, a machine learning algorithm builds a model by examining many examples and attempting to find a model that minimizes loss. So what is loss in this context? This is also called, this process of, the algorithm building the model and trying to minimize the loss is also called empirical risk minimization. This is just for awareness. Some people use this term, but we just want to focus here on loss. So what is loss in this case? So loss is the penalty for bad prediction. So it's a number that indicates how bad the model prediction was based on a single example. So we have here two graphs. So these blue lines here, or sorry, the blue arrows represent the loss, and then I'm sorry, the not blue. The red arrows represent the loss, and the blue lines represent the prediction, right? So you have X and Y. Let's say the X is your pixel values, and then Y you'd have your crop type or a class you want to predict. And it's the same here for the graph on the right side. And you can see that the arrows here on the left plot are much longer compared to the ones on the right plot. So that means that this model on the right side is predicting better than the model on the left side because you have a greater loss. Does that make sense?
There is one question from Steven in the chat. He's asking, what is a hidden network?
Oh yeah, okay. Yeah, we are gonna go through it, but right now, just quickly, the hidden network is where the model is gonna take our input data and assign those weights, like we saw yesterday on the video, where you had predicting letter C and D. So in the hidden layer is where are doing the model is doing all this weight assignments and using a function to get to your output. It's where the magic happens, but it's called hidden because we don't see it. And we're gonna talk about this because this relates to black boxes, what people call black boxes. So we're gonna talk about this. Does that answer your question, Steven? Because very quickly, but we're gonna. Okay, awesome. So we want a model that has very little loss, right? We want a model that predicts well. And this is just an example. There's many types of loss functions, but one of them, to measure the model loss is this mean square error. I'm sure some of you, if not all of you, have heard about this, but it is the average square loss per example over the whole data set. And you have this equation. You're basically just extracting y from the prediction x. And here x is the set of features, so the pixel values in our case, from the satellite imagery that the model uses to make predictions, and y is the actual label, let's say the crop type that we're looking at. So you sum all of that, you square that, and then you divide by n. N is the number of examples in your data set. So n would be, the sample, and d the population representative, and then prediction is like the function of the model. So this is just one example. Just this is a very commonly used one, so I'm sure you guys have used. So I just want to give an example of loss functions, but in real life, there's many other types of loss functions. Okay, so now we have neural networks, but people also use artificial neural networks. So just to differentiate, when people say artificial, they're meaning like, it's the very broad term that refers to any type of neural network model. And an important distinguishment here is that, ANNs can be either shallow or deep. And that's the image that we saw. Shallow meaning, they only have one hidden layer, right? And then the deep ones, they have more than one hidden layer. So in this example here, again, an example of cat and dog. It has this first layer here at the bottom is the input, and then it has three different hidden layers before it gets to the output layer. So this is considered deep neural networks because it has more than one hidden layer. That's the only distinguishment that you can make here. And yeah, deeply neural networks are what people are most implementing nowadays. So when people say like artificial neural network, is like just think about very broad, what is a neural network? So Neuron, we saw a little bit yesterday. So they are, just mimicking a human neuron. So they're the building blocks for neural networks. And, you can also think of them as the layer, right? So these are simple computational units that have weighted input signals and produce an output signal using an activation function. And we're going to talk about this. So again, this would be a neuron. So you have your input layer. This is where, the weights are assigned, and you have a function that will produce your output. So just imagine the pixels here getting inputted, and then the output, like the crop type of that specific pixel here. And here in the middle, you have your activation function, which is what we're going to look next or later. There are many types of neural networks architectures. You have perceptron, multilayer perceptron, backpropagation, many different ones. Convolution neural networks. This is the one that we're going to talk about later, because we will be doing this one. We'll be using a convolution neural networks, and we're going to see why we'll be using this. You also have UNets, many different types of architectures. We're going to go through perceptron, multilayer, a couple of these, not all of them. But there are many types, and they are used for different uses. This is just, a very quick schematic. We're going to look into perceptron, and, you have here in this green just the input layers. The output layers are in yellow, and then you have these dark blue ones as the hidden layers. And you can have many variations, right? It's just different architectures. We're going to talk a little bit about some of these. We're going to talk about recurrent neural network as well. So you can see that many variations. So the perceptron, this is the most simplified type of neural network. Is just one single neural network layer used in supervised learning. It is a linear binary classifier, so it just means that it's just linear. You cannot do any prediction based on non-linear features between the data sets. And again, this is just a different schematic of a neuron or a perceptron, if you want to call it. You have all your inputs here called X. Then you multiply them by your weights. Then you have the weighted sum, and then in the end you have a function, an activation function. We're going to talk about this to to have your output here at the end. And this activation function is sometimes called step function as well. So this is the most like simple type of neural network, if you may say. So what is an activation function? We saw in the drawings that what you use to get the output of a hidden layer or a node. So I'm going to be using, these terms interchangeably. So hidden layer also means node, which also means a neuron. And it's also called a transfer function as well. So you can see that, there are many types of names, and that's why I wanted to go through all these terms with you. These activation functions can be divided into linear, as we saw, but non-linear as well. And the main difference, like the main people use the deep neural networks because they can use non-linear features, and that's when you have a linear function, they are confined, so they do not help with very complex problems. So having non-linear, if you can use non-linear functions, that will help much more the model to learn about patterns and features. This again, I'm just giving an example. We're not going to go through all the activation functions, but one of them is called rectify linear unit, or ReLU, and this is commonly used in deep learning model. So it's very simple. The function will return a 0 if it receives any negative input, but for any positive value, it returns that value back. So it can be written as the max of 0 and then x, because if it's greater than 0, you return that x number. And you can see here just the plot of this ReLU function. And here an example, let's say this was a satellite imagery, and you have pixel values or something like that. You can see that for positive numbers it returns that exact number, but for negative numbers it returns 0. So there, as I said, there are many of these. We later, probably not in this webinar, but later on we're going to talk about sigmoid and Softimax, but there are many types. And there's this really nice video here that maybe this one I can play myself because I don't think we need the audio, but it's just a very cool animation of, okay. So it just shows the different, very quickly, but like the different types of activation functions. Okay, I think we got an idea. So you have many of them, and you're gonna use them, in different situations. We're not gonna talk about this right now, but just so you all know that there are many types of activation functions. And this is the same. It's just having the functions actually written here and not changing in a video. But we don't need to go through any of these. But you have the plot for them, and then also their derivative. So now we saw perceptron, but now we're looking into multi-layer perceptron. So it's very intuitive. We saw a perceptron only have one single layer. For multi-layer, you're gonna have more than one, right? So here is a schematic. So instead of having just one hidden layer, the multi-layer perceptron is gonna have more than one. And then in this case, it can distinguish data that is not linearly separable. So it does it helps with the non-linearity between the data. And it is also a type of feed-forward neural network. And so feed-forward, that's also another term that is commonly used. So what that means that the connection between the nodes do not form a cycle. So it only moves in one direction, right? It just comes, from inputs and it moves towards the output. There's no connection here between the nodes. And we're gonna see later one type of neural networks that does have a connection between the nodes. And another interesting thing here compared to the perceptron is that the multilayer perceptron uses backpropagation for training. So what that backpropagation is a method of fine-tuning the weights of a neural network. So it's basically learning from the error, right? You get a result in the end with your outputs, and then it analyzes that and changes those weights to have a better result. So that's exactly what we have here. You have your input layer, your axis, you have your weights here in your hidden layer. You have the activation function, which is going to generate your output layer, right? But then here at the end, you calculate, the error, or if you want to call your loss, right? Because we saw what loss is. And then this is traveled back to the hidden layers. The weights are adjusted so that you can minimize this error or this loss and then have better output. So that's what backpropagation means. You get an error here, you send it back, you adjust the weights to minimize the error, and then you get a better output in the end. Carlos asked how to establish how many hidden layers are needed. That's a very good question. And for tomorrow, we're going to do an exercise where you all be learning how to do that. It's going to be a drawing exercise, and I'm excited for that. But we're going to talk about that tomorrow, if you don't mind waiting, Carlos. But that's a very good question. No. Okay. Yeah. So be excited for tomorrow. You also have an objective function. Sometimes it's also called a loss function. So we talked about loss, right? And then we have a loss function. So it's kind of intuitive what this might do, but it's using the backpropagation. So what we just saw previously to optimize your model and its parameters. So the backpropagation you can think as the process of going back, and then the actual improvement, the optimization you can think about as the objective function or the loss function. So the goal is to minimize the error and then to maximize or minimize your objective. So and so this is where it gets confusing because it talks about propagation. The concepts start to blend. So if you have any questions, please ask. But and I said here sometimes it's called loss function. Some people will say that it's different, and the reason why it's different is that an objective function, it can maximize or minimize your objective or your number. You can think of this as your output. And loss function, it only focuses on minimizing your output. So basically, an objective function takes the data and model parameters as arguments, and then these then are evaluated to return the output it is supposed to return. So we cannot calculate perfect weights for a neural network, at first, right? There are too many unknowns. So instead, we use this algorithm to navigate the space of possible sets of weights that the model can use in order to make a good prediction. So let's say you have your objective here, your y line here, and then these are all the variables, and if you want to maximize that, you want to exactly this point here, right, the max of the objective function. So you can think of an objective function trying to maximize your output in this case, and it's to minimize the error. Okay, a little bit more complicated, stochastic gradient descent. We could go back all the way to gradient descent, but I'm gonna introduce directly stochastic one. So this is a term that is, very, it's commonly used And that is because it is a, it's one of the most, if not the most, training algorithms for neural network. And what this is it's an interactive method for optimizing an objective function. So we just talked about optimizing our weights, right, our parameters, and now we're talking about optimizing that optimization. So that's exactly it. We are optimizing the optimization. And let's start with stochastic. You also have the regular gradient descent, but stochastic here means that it uses randomly selected sample. And this is just because of a computational problem. If we were like looking into every single data point we have in our data set, it would take a long time, right? If we have like a massive amount of data. So stochastic, because we select just a couple of them, and that's just to reduce computation. So if you look here, for example, in this graph above, the lowest point here, occurs when x is equal 1. And the objective of the gradient descent algorithm is to find this value of x, so where like the y is the minimum. So that's what this function will do, is to look for this value here where the y is the minimum. And this is just a 3D type of plot, and you have the SGD, but there are other types as well, which is this momentum, the NAG, different ones. But it's basically, if you have a plot, is just trying to look for the minimum value there. We're not going to talk about these other ones. I just wanted to introduce, like, when you see stochastic gradient descent, you know that this is trying to optimize your objective function, and all of this is just to minimize your error, is to improve your model. Does that make sense? No, it's going to start to get a little bit complicated. I will take silence as a yes. So, and yeah, later on I will mention about the presentation exercise. You can just put all your questions, what you learned well, what you think you're still struggling in, and we can discuss that. And we will be touching a lot of concepts here, just so you all have the most basic like understanding and awareness of neural networks and everything that goes around it. Okay, so
sorry,
yeah.
just
Yeah.
just to jump in here and making naive questions, but at the end of the day, when we are doing any kind of those models with neuronal networks, then why should, so by doing it, we should try all of those neuronal networks, or should we go directly to SGD or to some? So what is the recommendation in practice?
Yeah, that's a very good question. It depends on what you're trying to model or predict. We're the next one that I'm showing is like recurrent neural networks. We're gonna see why, like, when should you use that recurrent neural network for satellite imagery, like for example in our case crowd mapping, and other cases as well with remote sensing. Most people use convolutional neural networks, and that's because it's more focused on image recognition. Like this multilayer perceptron might be better for like text, prediction, that sort of thing. But it really depends. I don't have an answer. Like I don't have a table. If you do, if you're trying to do this, you should use this. But we're gonna look a little bit into that. But we will focus on the convolutional neural networks, and we're gonna understand why we'll be using that. And then we have an example here next about the recurrent neural networks. Okay, so what are recurrent? By the name recurrent, you can think, it's going back, right? So it's a time series version of the regular artificial neural network. So they are meant to process sequences of data, And for in this case, they are at the basis of forecast and language models. So you can think about just as I said, text recognition. I don't know, maybe the translator, right? Google Translator, it will use recurrent neural networks to suggest a translation for you, right? Because if it uses a couple of words together, when you're like writing or speaking, if those words come together, you kind of intuitively know what the subject is about. So for recurrent neural networks, language model, language recognition is a good example. They will specifically choose how much past information they want to let flow through the model and how much they don't. So that's how people say that that's how they model memory, right? Because you access information from the past and you use in your model in the present. So here is just an image of a time series data set, right? You have your same scene. Let's say, I don't know, it's a Sentinel 2 or Landsat scene, but you have that same scene over time. So the recurrent neural network would access a pixel information, how it changed throughout time, and use that information to get an output at the end. So yeah, it captures the relationship across the inputs. So this is something we talked about feed forward, right? It just moves in one direction. But in the case of recurrent neural networks, let's say here in the X here at the bottom, those are your input layers. Then you have your hidden layers in the middle with your weights here, and then you have your outputs here at the top with the Y. So in the case of recurrent neural networks, these hidden layers are connected to each other. So instead of just going forward, they're exchanging information amongst themselves. So an information here from the past can influence the weight that the model is going to assign for this specific input here in this hidden layer. So they learn from prior outputs while generating the outputs. And this, you can think of a couple of examples. I'm going to ask this question next, but how this would be important in some cases in practice. So the outputs are influenced not just by the weights applied on inputs like a regular neural network, but also a hidden state vector, which would be this prior information that the model can access. So it's like it's not going only in one direction, it's like crossing as well. So, and that's what I want to ask. It's a good timing. So how do you guys think, and you can put the answer in the chat, how would this contribute to crop mapping in Cambodia? And you can think about the time series that I mentioned. How would that help with the crop mapping, having a recurrent neural network? Any guesses?
Andre?
Yeah.
Yeah, thank you for your presentation. I think for us, it's first, I think we can try using this machine learning to do the crop mapping for Cambodia. But first, we will start as the pilot site, in our project plan. We do the pilot in Rok Mandul in Ban Bong province. It is in the northwest province. Northwestern province. So right. I think the limitation for us are the diversity of the crop mix in one location. So right. Like you see in other countries, crop are grown in a very large scale, like commercial or industrial, But for us, there are so many still grown as the family, a small household. Yeah. So normally in the orchard we have small size and we have mix of crop in those small size orchard and even the nearby. So I think it can be very difficult for the machine and for us to especially for the machine to realize the in the in the input patterns of the each type of the crop. If you see from the satellite, then they may look alike, but actually they're not. They're different crops, Yeah.
Right.
But I think it can be very much rely on our field work to collect the data, of the exact location, the exact crop type, and input it to the model. Another limitation is that we have to work in the same period of time or season, So the crop can be changed even in its, phenological, growth performance. It changes over time, and some are seasonal crop. So if we see it this time of the year, we may not see it again next year, something like that. Depend on somehow very on the farmer decision, to grow the crop as well. But for rice, for Cambodia, rice is more permanently grown in the area. So I think we can be pretty sure with accuracy or precision of the rice crop. Yeah, but for the non-rice, I think it's maybe more a challenge for us. Yeah, but I think we should work best of what can we see on in the pilot site first. Yeah, if things goes well in the pilot site, for example, if we are going to do the field work to collect more representative samples as the input, then we run the model and see how we can have the result of the output. For example, the accuracy and the precision. But yeah, I think we don't know like what level of accuracy is acceptable and what level of precision is acceptable after we run the model with our our inputs data. Yeah. So thank you, Andre.
Yeah, thank you, Dr. Senvan. Yeah, that's exactly right. So yeah, that's the point I was trying to bring up here. So the recurrent neural network, because we have very similar crop types, even if in our pilot area, if the phenology, right, of the crop, if if the crop was that exactly crop previously in previous years, then you can use that information, right, in your model to predict what it is today. So um, for crop mapping, this would be very useful, right, using a recurrent neural network, because you can see the past information about that pixel, that polygon, that crop area that you had. So it would be very useful. But one of the limitations, besides all that you mentioned here in the case of using optical imagery, is that for time series, is that Cambodia, it rains a lot, right? So it's cloudy a lot of times, right? So it would be hard to use optical imagery in a recurrent neural network, because you wouldn't get many good images to input in your model. So that would be a limitation for Cambodia. Any other thoughts? Yeah, Maria agrees with Dr. Van Sang. Yeah, perfect. Okay. So yeah, this would
But
be
I would just can I just add something? So I agree completely with both of you about the limitations. But for me, I think if this looks promising in the testing or in the pilot province, for me, the most interesting aspect of working with the neural network or any kind of machine learning is that hopefully this will kind of reduce the workload of people in the future, right? I mean, my assumption is that once the model, if the model is good and we kind of select the model, and then we can just, not just, but we can run with it and constantly improve it, but it will be something that will make workload a little bit easier in terms of future mapping. So maybe faster to produce the information. But and this is what I wanted to kind of ask you: is this the case, or how does it? I mean, how does it compare? Like, for example, if you just do a time series data with like just the optical data, or even with a sentinel data, if you just do like a more simple time series analysis, like in terms of the workload, like do you have any insights from your experience so far?
Yeah, right, Maria, that's a great point. Yes, if you do have a good model, and by good model, I mean, you know, when you feed new data that it hasn't seen before, it should give a good output. So yeah, this is the case, and that's called transfer learning. You can use the same model but in different areas, and see, you know, if it does a good job. Regarding the time series, that is a drawback of the recurrent neural network, because yes, it does require it's a larger amount of data, right? Because you're not using only one image, you're using the time series of it. So it does get a little bit more complicated. We're going to talk a little bit about convolutional neural networks, which you know, deals with the huge amount of data, and some people kind of combined the recurrent with the convolutional. We're not gonna like go in depth about it, but you will understand um, how to like minimize the amount of data with the convolutional neural network. And yeah, Bore also added a comment there. Yeah, faster product data and save time. Yeah, thanks for sharing, everyone. Yeah, so that's the, you know, advantage of recurrent neural networks. You can use past data information, and I think for crop mapping is important because of phenology, right? You can distinguish the crops if you look into phenology, hopefully. So so it's almost been an hour. I didn't add like let's take a break slide at this time, but do you guys want to take a break before we go into neural networks? We're a little bit past the half here of my slides. We can keep going, or keep going. Okay, go ahead. Okay, so okay, convolutional neural networks. So it is the class of deep learning most used to analyze visual imagery, and you know, by visual imagery, we are also talking here about, you know, satellite imagery. And it was inspired by the organization of our visual cortex. So this, what it means, that, you know, individual neurons respond to stimuli only in a restricted region of the visual field, known as the receptive field. And then, you know, a collection of such fields overlap to cover the entire visual area. What this means is that, you know, when you look with your eyes, you know, your focus can be like in one part of what you're seeing, but you know, you can see like the um, around of it as well. So here, you know, the eye is looking, you know, you can see all of this area here with the zebra, but when you're looking, like your focus go, for example, in the nose of the zebra. So here at the bottom, I think you guys can see my mouse. it grabs just a small piece of what you can see, and then it assigns the weights. It goes to the next step that way. So instead of grabbing the entire image, the convolutional neural network, it grabs like just the small pieces, each small piece, and then goes through it. And then we're gonna talk about this. This is what is called a convolution. But the main takeaway from this slide is that instead of like having your entire image, is going to focus on the small pieces of the image. So yeah, what I just described kind of translates to this. It reduces the images into a form which is easier to process without losing the features which are critical for getting a good prediction. So as I said, it will grab, you have your input here. We're going to talk about all of these steps in a certain detail, but it grabs just a small piece. It transforms this small piece into a way that is you're gonna use less processing, less data, and it keeps doing that until you have your output at the end. We're gonna talk about these steps, but you can think about you have your convolution, you have pooling. We're gonna talk about these terms, convolution and pooling, and then in the end you have your fully connected layers. We're gonna talk about this, what's flattening, and also with getting the output at the end. But just think about the advantage of convolutional is that it turns the images into simpler forms, which will accelerate the processing. You're gonna have use less time to run a model with convolutional neural network, and that's why it focuses on image recognition, because it's what you can use it with. So why using convolutional neural network instead of the feed forward neural networks? Example, the multi-layer perceptron. The CNNs are able to successfully capture the spatial and also temporal dependencies in an image through the application of these relevant filters. We're going to talk about these filters. So the architecture performs a better fitting to the image dataset due to the reduction in the number of parameters involved, and also the reusability of the weights. So it's just like a faster approach. You can think that an image is nothing more than a matrix of pixels, right? So why not just flatten this image, meaning that you turn this 3x3 matrix into this 9x1 vector, and you can think, oh, maybe I'll just feed this into a multi-layer perceptron and see what the results look like. But it's not really, you won't really yield high accuracy when you have complex images with pixel dependencies. Like you can think as the time series that we talked about, or an image that have the pixels that depend on each other. So yeah, for a binary classification, just flattening the 3x3 image into a one vector, that work, but not for a satellite image where not only the pixels depend on each other. A satellite image also contains the different channels, right? You have red, you have green, you have blue, you have many other types of channels. So there's the pixels depend a lot on each other, right? You cannot like take this 4, this 9, and by 35 and separate them, right? They depend on each other because it's the same pixel. It's just different information of the same pixel. So that's why convolutional networks are in this case better than multi-layer perceptron, because it can capture this spatial spatial feature that a satellite image has. It keeps the information together. So what are convolutions? It's the formal definition is that it's a mathematical operation which describes a rule of how to mix two functions or pieces of information. So what happens is you have your input data or a feature map, and you also have a kernel, which these two mix together to form a transformed feature map. So if you think here of the image, which is your green, pixels here, you have a kernel, which is the yellow part here, which is a 3x3 kernel, and the image is 5x5. Convolution is it's just grabbing each area here of the kernel and assigning a new value. So it multiplies the pixel values of the kernel values and then sum all of them together. So it's kind of hard to see because it's moving. We're gonna see more animations to make it easier to see. But the pixel values are the one in greens and the kernel values are the one here in red. So it's just multiplying these and assigning, summing all of these together to assign a new value here. And it does in this direction. It starts here at the top on the left side and it goes to the right and then goes to the bottom and goes to the right again. So what it's doing to the image is it's reducing, right? It's reducing the image into a smaller feature, but it can still store the information that you need, right? So it's not like destroying your pixel here, your image. So it's just transforming into a smaller feature, and that's where it comes like the faster processing. So this is just one example of what our convolution. You also have this kernel, which you can think of as the filter that we have mentioned before. So this is another example. I'm sorry, the animation is super fast, but this is your kernel here in the middle, and what it's doing is just multiplying, these values together, and in the end, it's summing here, and that's where you get your output. You can see that in this case, it's using numbers here that are not exactly in the image. It's like above and on the sides, and we're gonna talk about this later. But this is just an animation showing what's a convolution. You have a filter that will change the information you have without losing that prior information. So the objective of this convolution is to extract higher level features such as edges from the input image. So you can see this is an example. You have this cute animal here as the input image. You have your kernel, and then the result of that is you sharpen all the edges. That's the objective of a convolution. It's extracting these high level features here without losing the main information. So you have less data here because you have less color, so that's less data, but you still can keep what's relevant. In this case, it's the edge of the animal. So that's why you use a convolution. And here is just showing that movement that it goes. It starts here at the top and then goes to the right, it goes down, and it does all that movement. Okay, so more terms here. You have a stride, which is how much the kernel moves to the right. So in these two examples that we had here, so this one, it's moving 1 pixel at a time, right? It's moving to the right 1 pixel at a time. But you can also have a stride of 2, which is this example here at the top. Instead of moving 1 pixel at a time, it's moving 2 pixels at a time, right? So this is stride of length 2. And then you also have padding, which is what I mentioned before. So padding is it's when you have two types. You have the valid and the same padding. So valid is to reduce in dimensionality, and then same padding is the same or increase in dimensionality. So it's basically just adding these pixels here around, and when you do that, you can either reduce or keep or dimensionality, and it depends for what you're using, but the point here, stride is how much you move to the right, and padding is this pixels here on the external. So in this case here, it's padding with zeros, and it's creating a 6x6 instead of a 5x5, which we had originally. It depends on what you're doing. I think most of the case we're gonna reduce the dimensionality because we wanna be able to process faster our model. And you also have pooling. Previously, we saw in the example of a neural network, we had convolutional, we had pooling. So pooling is very similar to the convolutional layer, but the pooling is responsible for also reducing the spatial size of the convoluted feature. So again, it's all focused on decreasing the computational power required to process the data, and it's also useful to extract dominant features. And there are two types: average pooling and max pooling. It's very intuitive. So let's say here you have your pixel. Max pooling is gonna, here in red, is gonna extract the max of these numbers. So it's gonna extract 20. Same case here for the yellow, the blue, and the green. Average pooling is gonna extract the average of average of the portion here. Another thing, I haven't added it here, but max pooling also perform what is known as a noise supersent. So it discards the noisy features altogether. It acts like a denoising type of dimensionality reduction. So most of the times, max pooling is more used than average pooling. But the main point here is just, we are using this to just make our data smaller and decrease the computational power required to process everything. So this is a very simplistic workflow of a convolutional neural network. You have your convolutional layer, then your pooling layer, and these two together, they successfully enable the model to understand the features. As we saw, we can extract edge features from the images we're looking at with the convolutional layer. And then, we can reduce the size of the image with the pooling layer, also extracting important information. And, when you think about edge, also think about the crop polygons that we are looking at, or crop mapping. We extract information about that, the shape of our crops and all of that. And then later we're going to look into now flattening and then fully connected layer. So these two they make all of these pooled layer into a one-dimensional layer, so that it can be the input for the classification. So you can look at this as these two steps here. They are just the feature engineering kind of step, feature extraction. You extract the most important information. You make that information small so that you can run fast. And then later you input this, you transform this into a flattened layer, so you can run the actual classification to get your output. So this it's another plot showing. Here you have a little car. As we saw, the convolutional neural network will look just into very small amounts of the entire region. And then you have your convolution, where it's extracting the edges. You have your pooling, which is making the data smaller. Another, here in this case, it's showing another layer of convolution plus pooling, and then in the end you flatten. That's this is more similar to what we saw before, right? You have all the inputs next to each other. Then you had the weights and activation functions and all of that, so that's called fully connected. And then you finally run your activation function that we talked about. In this case, it's showing here softmax, but it can be any other type of activation function. And then the output here, it's guessing like car, truck, van, because of the image here of a car. But so the main point here is, all of these like convolutions and pooling is the feature learning, right? It's extracting, it's making it smaller, it's making it faster, easy to treat, and then later you actually have declassification. So that's what a convolutional neural network is. Any questions about before I move on? There's a video The next one is a video that I want you guys to watch it. I think it's gonna, if it was too much, this might help understand a little better the feature learning process. So I have this video here. I want you guys to watch from, it's a 6-minute video, but we can focus only on, starting on minute 126 until 4. And it explains. So I posted here on the chat, that's 2.5 minutes. So I'm gonna count here and you guys can watch and then we can see if anyone has any questions. Feel free to put on the chat or let me know if everyone's done. Okay, we have Carlos responded. I'm not sure if you all decided to watch the whole video. So I got a couple more yes, then I can proceed. And also feel free to let me know if it was helpful or not. Good. Okay. Okay, I shall continue then. Interesting video. That's good. Okay. I hope it helped get the concept a little better. So the next basic concept, yeah, it's still basic. Helpful, show the goal. Okay, perfect. Thanks for sharing. And we can, as I said, we can come back to this. We're gonna do some exercises tomorrow, like demos, like play a little bit with some demos, which I think will help understand better some of the concepts. Yeah, so that's so great, perfect. Okay, good. So the next term that I wanted to talk about is inference. So what this means is that you're just applying your training model to unlabeled examples. So it's pretty much, we talked about like back propagation, right? Backward learning, which is going back and getting your errors and applying to adjust your weights. Inference, what it means is that you're just applying your model and moving forward. So you're gonna see inference used a lot, and that's why I wanted to introduce this term. And it's just you use your trained model to make useful predictions. So it's just making the classifications. It's different from training. Training it's just training, right? Inference is getting the final output, like the actual result that you want. Usually training, you use a large data set, right? A large number of images, and then you do this process of looking at the error, going backwards, fixing your model, fixing your weights. But the inference is when you have defined already your model, right? What we talked about, test set or validation set, and it's usually with a smaller number of sample, and then that's where you get your output. So inference, you're going to be hearing a lot about inference. Now, overfitting and underfitting. I know we mentioned at the very beginning overfitting, and I said I would touch again. This is the moment. So a model is said to be good if it generalizes any new input data from the problem domain in a proper way. So it's if you think about crop mapping. Let's say we have a crop mapping model. It's good if the output will always be a crop that makes sense, right? If it outputs something like water, we don't want that, right? It doesn't make any sense. But a good model will always make a good prediction about the data when you feed it new data. Underfitting means that the model does not capture the underlying trend of the data. It doesn't capture at all. Like the water would be an example, or something totally like not connected to what you have, to your training set. And then overfitting, that's the opposite, right? It's when the model matches the training data, which in this case is usually limited. so closely that it fails to make the correct predictions on new data. So overfitting what basically means that it's too good to be true. When it gets the training data really well, but then when you use on a task set, the results are not so good. So it gets acquainted with the training data a lot, but then when you try with a task set, it doesn't do a good job. So it's really it matches the training data too much. This is a visual example. I think it's easier to understand this way. So under fitting, you can see, here we only have a binary classes, so just circles and crosses. Under fitting, is not doing a very good job in, separating these two classes, so it doesn't do a good job at all. The good model, you would separate for a certain level, the circles from the crosses with some errors as well, because it's not perfect, right? And then overfitting is, it's too good to be true, right? It's doing these, like, it's exactly doing what it is expected, like 100% accuracy. That's not a real world example, right? You're always gonna have one or two misses there. So this happens because the training data is not well, you have flaws in your training data. So then when you train it with, the training data does a very good job. But then when you try with new inputs like the task set or the validation set, then the model doesn't do a good job. So some techniques to reduce overfitting. These are only two of them. There are many others, but I just want to talk about these two. One is increasing your training data set. So let's say, like, an example here would be that, maybe you're feeding too much of, too many like cassava crop types and not as much, I don't know, rambutan, data. So that's an issue, right? You need to increase, for example, the number of rambutan, or, just the training data in general, all types of crop types. The other technique is what is called dropout process. So you're gonna see a lot of models that use dropout process or not. And what this means is it ignores some units, some of the neurons. So you can see here on this representation here, instead of having this neural network, going through every single neuron, the dropout process is going to skip some of these neurons during the training phase. So they're just not considered, not going forward, and not in the back propagation either. So they just skip, and this forces the neural network to learn more robust features that are useful in conjunction with the subsets of the other neurons. This is a good way. It's an alternative to not have to collect more training data. So the dropout process is, when maybe you're limited to collect more training data, you just use the dropout process to try to improve your model accuracy due to overfitting. Yeah, another terms I wanted to, just touch here, because it can be really confusing when you're talking about this, is, classification versus object detection and image segmentation. These are terms that pop out a lot when you talk about neural networks and machine learning. And I think, this is a very good representation of the differences between them. With classification, the goal is simply to identify which objects and other properties exist in an image. So in this case, it's just a bird, right? You classify this as a bird. With object detection, you go one step further, and then you find the exact positions of those objects. So you have bird 1, and then bird 2, and then image segmentation is like even further, right? The goal is to recognize and understand what's in the image at, the pixel level. So every pixel in an image belongs to a single class, as opposed to, the object detection, where these bounding boxes can overlap. If they're close to each other, they could be overlapping. with image segmentation, you classify every single, pixel here. So this is what we'll be doing for, when we look into a satellite imagery. We want to classify every single pixel, right? Give it a label, a crop type, or a land cover or a land use. So I just wanted to call, just emphasize the difference here of these terms. So we'll be doing image segmentation. And this is just a table. I know, Carlos, we talked about, like, I don't have a table containing all the information, like which, how many hidden layers. We're going to look into it tomorrow, how many you should use. But this is, it's not always true, but it's just a summary of, if you have sample points or polygon samples, the types of neural networks you can use. We didn't talk about UNet. Maybe tomorrow I can present it, but also the type of the data you have, if it's continuous or categorical. For us, it would be categorical because we have classes. And then, which neural net to use, which type of loss function to use, and activation function as well. And then number of nodes, which, are the neurons that we talked about. So there are some stuff out there, but, in a lot of cases, it's really like trial and error. And some of them are going to be good for some cases. Some of them are going to not be good at other cases. But it's just, I just wanted to show this as a summary. You don't need to worry about this now. And then finally, some advantages and disadvantages as well. So one of the things that, increased like the popularity of neural networks is it gathers a massive amount of data, right? Over the last years and decades, people have been using neural networks more and more, and it gives better results when you gather all the data and information, whereas like traditional machine learning algorithms, they will reach a level of accuracy where if you add more data, it just doesn't improve the performance, right? So that's compared to like classical machine learning like random forests or just simple decision trees. You can add data until a certain point. After that, if you add more data, the model does not improve. So with neural networks, if you feed more data, you always learn more and more and more. And that's one of the reasons. That's one advantage of neural networks compared to classical machine learning models. Also, they can be flexible. They can be used for both classification and regression problems, not just one. They're very good to model with nonlinear data with large number of inputs. We talked about the advantage of using nonlinear data instead of linear. You can gather more features, more similarities. Once trained, the predictions are relatively fast. So yeah, the training process is the one that takes longer, but then once trained, the predictions are usually faster. And we talked about also transfer learning, right? Using the same model to different situations if it's a good model, a well-trained model. It also has the ability to work with incomplete information. It also does a good job with, like, if you think about like unsupervised learning, right? It learns without the labeled data. And then parallel processing, right? It's faster. Like things are happening at the same time. It's not like you don't have to wait for one level of like layer to finish to run the other. So parallel processing happens, which makes the modeling faster. These are just some of the advantages of the neural networks. And then some limitations, right? Because not everything is perfect. So no free lunch theorem. What this means is that this theorem is a result that states that for certain types of mathematical problems, the computational cost of finding a solution, average over all the problems in the class is the same for any solution method. So what it's saying is sometimes it doesn't pay off, right? Sometimes this computational time that you're gonna spend is just, it's just better if you did a simple model, right? It's not gonna pay back in the end. Also, another limitation, it's very sensitive to data inputs, and again, it requires a lot of training data, right? It's not gonna do a good job if you have a limited amount of data. So you need that massive amount of data so it does a good job. Otherwise, if you don't have, it's just better to use like random forest or another type of model. Also, and we touched a bit. Carlos asked, it requires the correct model type architecture for the problem. If you're not using a correct structure or model architecture, it's not going to do a good job. So we need to think about which neural network type is the best one to use for our type of problem. Talks about like recurrent neural networks. We talk about time series. Maybe that's a good one because we're dealing with crop phenology here, so time series and that sort of stuff. Another drawback, computationally expensive to train models, right? Some models take like hours, right? Like half a day to train, depending on the computer, depending on where you're running your model, if it's in the cloud and all of that. And another thing, I mentioned this before, it's considered a black box, right? Because sometimes you don't know why an output is that output, right? It just delivers the results without an explanation of how the results were derived. We talked about all those, processes that happen in like a neural network, and pooling and convolutional and like activation function, optimization functions, objective function. But like in the end, it's not really explained why you got an output. So it is difficult, or basically impossible to explain how decisions were made based on the output of the network. And I like this chart because it's this guy, oh, this is your machine learning system. It's just a pile of like everything mixed together, right? And then he's like, yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. And he's like, what if the answers are wrong? And then he's like, just stir the pile until they start looking right. So this is pretty much like an approach that a lot of people use. They want to use machine learning, but these neural networks, but we don't really know, like we don't really have an answer when we have sometimes an output and there's no explanation for that, and then people just adjust the weights, right? They just adjust which function they're using or which type and try to see if that's a better result. So that's a drawback. It's considered a black box compared to like the decision tree. You can check the decision tree, in every single detail and infer why, the output is the output that it got. So these are some of the limitations. So for tomorrow, we're gonna do a little recap of today, because I know we touched a lot, like in a lot of different concepts and terminology, and it can be really like overwhelming. So we'll do a quick recap of everything we learned today. And again, the purpose of this is that you have the broad general like basic understanding of all the terms that I used and how those neural networks model work at a basic level. And then I, as I mentioned yesterday and today throughout the presentation, I do want you guys to prepare a presentation with like everything you've learned, anything you are having trouble understanding, any questions you might have, so that we can have a discussion. The way we can do this, we can divide, I think, into the teams that are already, like we have the FAO team, we have MOE, so we can divide into those teams, or if anyone has any other suggestion of how we should divide. But if that sounds good, we can do that way, and each group can prepare a presentation, lessons learned, anything to discuss, questions. And then we are also later after we're gonna do these neural network demos. So we're gonna play with TensorFlow, which I'm gonna introduce tomorrow, but we're gonna focus more on the last day, where we're gonna talk about the tools that are used to run these models, like TensorFlow, Google Colab, Google machine learning, all of that. And then we're gonna play with, how many inputs you add, how many hidden layers you're gonna add, the ratio of training. We're gonna talk about learning rates and all of that. So new concepts to be introduced. And here, how many hidden layers should we choose? So tomorrow is more, participation of you guys. So does that sound good? Bringing a presentation, and then we can, go over the presentations and all of that. And if you have any questions, we have, I think, 10 minutes left. And I will add the recording to the same website that has been shared. Does that sound good?
So sorry, Andre, I missed your your few slides. So the plan for presentation and discussion, is it a group presentation discussion, or what kind of presentation are you expecting?
Yeah, so just putting a presentation with what you've learned, or any questions that you might have, any points of discussion. If you want to go, you want me to go over, some concepts you couldn't quite understand, but just putting together a presentation about what you've learned, and we can discuss that. And the groups, they can be, your work groups, for whichever way you guys think it's best to organize these groups. Okay.
Yeah, can I ask a question?
Yeah.
About the presentation. So because if we say a presentation, it's really, I mean, it can be like 10 slides or 1 slide. So maybe we can just ask people to kind of maybe write a few things that they think that they learn, and maybe how they think that they can use this. So maybe just focus on that. So maybe just a couple of slides, right? We are not asking them to prepare overview of neural networks or right. So maybe we can explain a little bit what we want out of the presentation, right? Because we just more of a understanding what everybody thinks until now, like how is this applied to your work. So maybe like how do you think you can use this in your work?
Right.
Does that sound okay?
Yeah, that sounds perfect. Yeah, like why we're talking about all of this, why it's relevant, because that will tell if they understood why we're doing this, right? So yeah, that sounds great. Yeah, and so Tan asks, it can be GDA and MOE. Yeah, it doesn't need to be like a lot of slides, just a couple of slides. I don't want giving a lot of work to you guys for just one day to prepare.
Do you think it's do you think, does everybody think they can prepare something, or maybe like the two teams, do you think you can prepare a couple of slides? Or we'll see tomorrow, I guess. We'll see whether we'll have presentations or
we're
okay.
Play with
we
the
can
demos.
do that. Yeah, I mean, if people
with the demos,
if people have time, it would be good.
Yeah, for sure. Yeah, and the demos, I think you help as well.
So, Andrea, how do you have the Khmer word "Kun"? Thank you underneath the thank you. Google Translate.
I'm sorry.
The
You have
Khmer
the
word.
Khmer.
Oh
the
yeah,
Khmer.
it was
Yeah,
Google
thank
Translate.
you.
Yes.
Is it Google Translate or what? It's
Yes,
read
it is
well.
Google Translate.
That's good. Yeah. Oh.
It's their machine learning model telling me to translate.
Yeah, I think here we have the suggestion from Miss Borey also. Yes, a discussion,
Yeah,
not
okay. Yeah,
presentation.
that
Yeah,
sounds good.
I think that's good. Yeah.
Okay, no worries.
Yeah, we can do that.
Yeah.
We can prepare a few questions like for you guys to reflect and maybe kind of find a way to maybe give you some time for each question tomorrow to get some ideas. And yeah, no need for presentation. I agree. Yeah.
Okay.
It may also help to stimulate our discussion, and if you could have, prepare some guiding question, a few questions for us, like so that we can, everyone participated, and yeah. Thank you.
Yes. Yeah. Sounds good. Yeah, thank you. Thank you for the suggestion. Okay, so I think I'll see you guys tomorrow.
Great. Yeah. See you all tomorrow. Thanks a lot, everyone. Yeah, thank Andre. Yeah. Have a good rest. Yeah.
Thank you. Have a good day.
Yeah.